Okay, so now we're going to have some conventions here. I'm going to allocate R29 for this as the stack pointer. So let me say a little bit about what a stack looks like. A stack is just a big array in memory. So here's my memory, and I'm going to put my low addresses down here. And this is going to think of it as a stack of words. So these are consecutive words in memory where the addresses are growing up. Now, it may bother some of you that when I said up, I drew a down arrow. And I just have to tell you, I'm very sorry, but generations of computer scientists have always written low addresses at the top of the board and high addresses at the bottom of the board. So up in addresses is down in gravity. So what can I say? So you can see our little screen beam here is puzzling over how up became down. But just so that you're clear, this stack is growing up in addresses, and we always draw that, sadly, down the board. Okay, so R29 is going to tell me what the next location in the stack that can be used is. So locations that are below whatever by R29, I mean, if I looked in R29, I would find a number, and that number is the address of this location. Just to be clear what I meant there. And all of these locations here, which have addresses that are below the number in R29, okay, are locations that have already been used on the stack. If I want to use a location on the stack, I can. All of these guys are free. So these are used. And these are, or maybe free is a bad word, available. They're free for you to use. They're ready for you to use. Okay, and the convention is you can put something on the stack at any time. Any fragment of code can suddenly put something on the stack, but it has to remember to take it off again when it's done. Because the expectation is at any moment that, that if you put something on, it's up to you to take it off. If you leave it on, you're going to confuse other people who expect to find their thing at the top of the stack, because last they knew, that's where it was. So the convention is, you're running, you put some things on the stack, I'm running, I put some things on the stack. When I'm done, I have to take them off again before you get control back, because I want to make sure the stack is just the way you left it. Right? So there's a sort of this convention about that we're going to follow in our course, that's often followed, is that my job is to leave pretty much things exactly the way I found them. My job as the procedure is to leave things exactly the way I found them before I return to you. So you should expect everything to be just the way it was when you called me, except for R0, whose value is going to change. Yes, sir?
How do you guarantee that arguments you already have stored in register while you don't actually fill up the stack and start overwriting?
Well, what you're worried about, if I keep using the stack, am I going to run out of stack? And that happens in real life. I mean, if you go off and write a Python procedure that does a recursion depth of, say, 300, you'll get an error from the Python execution system saying, wait, I'm out of stack. And so you can run Python with a bigger stack. Most operating systems have a way of adding additional storage, not in terms of moving the addresses, but it says, look, I'm going to give you 500 locations of stack, and then you use more than that. It says, fine, I'll give you another 500 locations. It's sort of like making a disk file bigger and bigger and bigger.
Where are those stacks?
Where are those locations? Well, memory is big. We have, how big is our address space in the beta? How big is our addresses, our memory addresses in beta? 2 to the 32, so that's 4 billion bytes, okay, or 1 billion words. Right, so if you need more than that, you probably can't run on a 32-bit machine, sorry. 64 bits gives you a bit more than that to work with. And later on we'll talk about memory layouts. So there's some issues there, but for now let's just assume that we've arranged for there's plenty of room to do the activation records we want to store. Okay, so we're going to use software conventions. Notice the only thing we've really done is to allocate one of our registers to be the stack pointer. But that just means we're going to use that. There's nothing special about the hardware. R29 is just like R27 and R28. Okay. all we're doing is just setting this aside, and the compiler will follow the convention that whenever it wants to put things on and off the stack, it will use the R29 register to remember what locations have been used and what locations are available. So here's a bunch of little macros that we've written using our macro capability from last lecture that actually expand, okay, into little sequences of instructions, of beta instructions. So if I want to push something onto the stack, what's the convention? Well, first I have to sort of give that stack location to myself. So what I'm going to do is to take the stack pointer, which was pointing to here, and add 4 to it. So now the stack pointer points down to here, and I've allocated myself now this word to use, this word right here. The one that used to be at the top of the stack, I've moved the top of the stack down 1, and now I can go ahead and fill up this guy with whatever value I want. So you can see there's an add that moves the stack pointer higher into a higher address, allocating this memory location. Now I can move something into it with that store instruction. Pop does the opposite. It takes whatever was at the top, it takes this word, puts it in a register, and then moves the stack pointer down 1. And so what we have is sort of a push and pop are the opposite of each other. Push takes a register value and puts it onto the stack, and pop takes something that's on the stack and puts it back, puts it into a register, and both of them either make the stack pointer go up in memory or down in memory. Everybody sort of happy. So just think of this as a big array, and we're just sort of using the end of it to push and pop information. Yes, sir? We haven't talked yet about, I'm setting up this data structure, and now I'm about ready to show you what we're going to do in terms of actually procedure call and return. So that's a great question, and I just want to finish. We have ways of allocating a bunch of words on the stack at the same time, just moving the stack pointer by a whole bunch, or deallocating the same bunch of words. These orders, the order of this addc in the store and the order of this load and this addc, are carefully chosen. Now, we don't quite have enough information to understand why the order of those two instructions is very important, but I'll give you just a 10-second hint. What happens here is we're very careful to move the stack pointer, to allocate the location before using it. Suppose I did it the other way around. I used it and then I moved the stack pointer. Well, you could say, well, if those two instructions are one right after the other, would it really matter? I mean, I'd use a different offset on the store because I haven't manipulated the SP instruction yet. Would it really matter? And the answer is yes, if somehow the execution of the sequence of instructions was interrupted between this instruction and that instruction. If they were in the opposite order, I would have put something on the stack, but because I haven't changed the stack pointer, that location would still appear to be free by our convention that SP points to the first unused location. And we haven't talked about interrupts and the notion of suddenly stopping execution between any two instructions and going to do something else, but we'll get there. Meanwhile, we carefully arranged these macros to be in the correct, to have the instructions in the correct order, that we're always following stack discipline. We always allocate a location before we use it, and then on the pop, we always finish using it before we deallocate it. Okay. So stacks are pretty good. I mean, if we're running along and we suddenly have to do this exciting little program. This, by the way, is a capsule summary of about 1/2 of the Star Trek plots, which seem to involve some crisis involving dilithium crystals, which lasts for an entire hour, and then disaster is averted just after the last commercial. So, but the notion is, I have a fragment of code here that needs to use R0 and R1. I don't know whether R0 and R1 are being used anywhere else in the program, but I don't care because I can save their old values. Those two pushes put R0 and R1 on the stack. I can now go ahead and use them because I've saved away the values that were in them. And when I'm done, I pop them back out, right? So everybody's happy. Whatever the value, when I'm done, whatever was in R0 and R1 is now back in it, even though I've borrowed them temporarily for a set of instructions. And notice that the push and pops happen in opposite order. I pushed R0, I pushed R1, and then when I pop them, because now the stack pointer is here, when I pop them, I'm going to basically pop in reverse order. And that's what the last in, first out discipline is sort of all about. Okay, so this is, a long little slide full of bookkeeping. What I recommend we do is just focus on the use of these three registers. So I'm going to rewrite my little list of registers here to be slightly more coherent, to remind us what we're doing. So we're going to have R30, the magic R30, which you've been carefully avoiding and will continue to avoid for about 2 more weeks. But meanwhile, don't use R30. You'll see why. But then there's R29. What was R29 in our convention? That's the thing that's keeping track of where we are in the stack. So that's the stack pointer. R28, what was R28 going to be in our convention? That's what the return address goes into, right? So that's going to be what we call the linkage pointer. So these are just nicknames for these particular registers. And then we're going to have one more register that we allocate called the base of frame pointer. And you don't say, well, how many pointers do we need, Chris? Well, this will be, we'll need these, it's these three things here, and then along with R0, which is sort of the return value. So these are all the conventions that were, the registers that we'll use to implement our procedure call and return conventions. And you can say to yourself, well, Chris, what have we done? You've taken care of where the return value goes, and you've taken care of keeping track of where I have to return to once I'm done execution. The procedure is done execution. Okay, you haven't talked to me about arguments yet and things like that, so we're about ready to do that. Okay.